Hello and welcome to our next module on linear block codes. Let's start with a brief outline of today's talk. We will discuss a very important and practical aspect of linear block codes, which is the probability of residual errors. We will also talk about coding gain. We look at Hamming bound and look at something called as the notion of perfect codes. But let's start with a quick recap what we have done so far. We have covered in the last lecture topics related to erasures, errors, cosets, standard arrays, syndrome decoding, and we looked at several examples. So very quickly, we have realized that a channel can have both errors and erasures, and you can model such a channel with T errors and R erasures occurring for every code word. And the question is, how many of these can you actually correct? So if R erasures occur, what it effectively does is it reduces the minimum distance of the code. You have R fewer symbols to work with, and consequently in the worst case your effective D star, the minimum distance, becomes D star minus 1. So the erase symbols have to be simply discarded. We looked at a simple example where we saw that in order to correct for T errors, you now must have D star minus R, which is the effective minimum distance, greater than or equal to 2T plus 1, or you can have D star greater than or equal to 2T plus R plus 1. So your erasures eat into the number of errors you can correct. Okay. Suppose your channel does not have any errors, it has only R erasures, then D star should be greater than R plus 1. Now we also looked at cosets, and we defined for an n comma k code over GFQ, if A is any vector of length n. What is n? N is the code word length, also called as the block length of the linear block code. Then A plus C is called the coset or the translate of C, and A and B are said to be in the same coset if A minus B is an element of C. So we have looked at some properties of the cosets, and every vector B of length n is in the same coset of C if we have each coset contains exactly q raised to the power k vectors. Two cosets are either disjoint or coincide, and A plus C is a coset of C. If B is an element of A plus C, then we have B plus C is equal to A plus C. So we have already looked at these properties. We then defined a notion of a coset leader. What is a coset leader? It is a vector which has the minimum weight in a coset. It is called the coset leader. We will identify the error with that. If there are more than one vectors with minimum weight, then one of them is chosen as random. What do we do with a coset? We form a standard array based on cosets. So what is a standard array? The standard array for an n comma k code is nothing but a table. How big is the table? It is q raised to the power n minus k cross q raised to the power k. So this table, the size of this table increases exponentially as k and n minus k increases. So the first row of the standard array consists of the actual code words, starting with the all 0 code word on extreme left, and all other rows are cosets. Okay. Then we talked about something called as a syndrome decoding. For that we defined the syndrome first, where if H is the parity check matrix of an n comma k code, then any vector nu which is an element of this GFQN is defined as S is equal to nu times H transpose. This S is called the syndrome of nu, and sometimes it is explicitly written as S of nu. It is called a syndrome because it gives us the symptoms of the error, thereby diagnosing the error. Okay. If you remember, if this nu was the real code word C, the valid code word C, then CH transpose would be 0. So the syndrome is 0 by definition for an actual code word. What do we mean by syndrome decoding? Well, first we all find out the syndrome of any received vector nu, and then we locate the syndrome in the syndrome column and determine the corresponding coset leader, which is supposed to give the error vector E. We subtract this error vector E simply from the received vector to recover from the errors and give our correctly decoded word Y. Now we talk about the probability of error. Now please note, the aim of linear block codes is to recover from errors, but they are not foolproof. They can correct for errors for which they have been defined for. They have been designed for a certain number of errors, and they can only correct up to those many number of errors. So there is a probability that more number of errors occur in a code word more than what it has been designed for. In that case, your error correcting code cannot recover, and hence it leads to some residual probability of error. So the probability of error, or p-error, for any decoding scheme is the probability that the decoder output is a wrong code word. Despite our safety net, despite this mathematical insurance that we have put across, we still can make errors. This is called the residual error rate. What does it mean? Despite applying error control coding, we still get errors, and that is the residual error rate. Now let us look at the probability of error. Suppose there are m code words, each one of length n. So we are talking about a linear block code of block length n. These code words are used with equal probability. Then suppose you do a standard array based decoding, and please note, this analysis will hold true for syndrome decoding as well. Let the number of coset leaders with weight I be denoted by ai. We assume that there is a binary symmetric channel with symbol error probability small p. So a decoding error occurs if the error vector is not a coset leader, because that is how we defined error correction based on standard arrays, that the coset leader is designated as that error, and we correct for that error. So the probability of correct decoding will be given by p correct as a summation I is equal to 1 through n alpha I pi 1 minus p n minus I. So probability of incorrect detection, the probability of error is just 1 minus the probability of correct detection. So let us now have m errors in the block length of n bits. So m is necessarily less than or equal to n. So how many errors can we correct? Well, it depends on the minimum distance of the code d star. So we know that the number of errors that are correctable are up to this integer less than or equal to half d star minus 1. This comes from the fact that d star should be greater than or equal to 2t plus 1 for correcting t errors. So we flip it around and we put that number of correctable errors. Then probability of n errors in a block of n bits is given by n choose m, because m errors are there. This is the probability of making one error. So we have m errors, so p raised by m, and at the same time the n minus m symbols must not be an error. So probability of not being an error is 1 minus p, so you have 1 minus p raised by n minus m. This is the probability m comma n, which means the probability of making m errors out of the n possible symbols. The code word will be an error if more than t errors occur, where t is the designed error correcting capability of that code. So how do we upper bound the probability of code word error? It is given simply by all the cases where m is t plus 1 or more. Here we have found out what is the probability that m errors occur in a code word of length n. Now up to m is equal to t errors can be corrected, but t plus 1 up to n, all such errors cannot be corrected by our linear block code whose d star is such that d star is greater than or equal to 2t plus 1. So, we have this upper bound by summation over all m's from t plus 1 up to n. We note that Pm cannot be less than the probability of erroneously decoding a transmitted code word as another code word which is at a distance d star. So, what we mean is that this Pm, right, here m goes from d star by 2 plus 1 up to d star is the errors. So, d star choose m is the total number of combinations, and then we can find the corresponding upper bound for m minus 1 code words. So, this approach says that we go code word by code word. There is a case where you have the closest code word to be only d star away from this received vector. Now, all code words that are distance at least d star, because there will be several code words which are more than d star. D star represents the worst case scenario. So, just look at the code words that are exactly at a distance d star or more. So, when we have at least d star, then we can put a union band as follows: Pm is less than or equal to m minus 1, m goes from d star by 2 plus 1 up to d star, and these are the number of ways to choose m out of d star. Okay. Probability of flipping a bit raised to m 1 minus p d star minus m. So, let us look at a simple example. So, consider our simple example of 4 code words in this code C: 0000, 1, 0, 1, 1, 0, 1, 0, 1 and 1, 1, 1, 0. We build the standard array with its own coset leaders. Each row is a coset. The first row is the valid code words, and here we have a column of syndrome. So, if you receive any one of these 4 and you apply new H transpose, you will get a 0, because a syndrome for a valid code word is always a 0 vector. But if you get any one of these 4 received vectors new, then new H transpose will always result in 1 1. Similarly, if you get any one of these, you will get 0 1, and for any one of these you will get 1 0. So, one syndrome corresponds to one of the coset leaders, and these coset leaders are the error vectors. So, you have now these coset leaders as 0 0 0 0, 1 0 0 0, 0 1 0 0 and 0 0 1 0. So, therefore, if you plug in the values, you can get the probability of error as 1 minus parenthesis open 1 minus p raised to power 4 plus 3 p 1 minus p raised to power 3. We just plugged in the value for p error, right. So, please note that this code has 4 code words and consequently can be used to send out 2 bits at a time. So, what does it mean? Well, you have 2 options, either you do coding or you do not. So, if you do not perform coding, the probability of error of 2-bit message being incorrectly received is nothing but p error is equal to 1 minus p correct is 1 minus p whole squared. So, 2 bits being received incorrectly. So, if you have small p which is flipping of a bit as 0.01, the word error rate upon coding is given by 0.0103, just plug in the value, while for the uncoded case it is 0.0199. So, if you see, we have almost halved the word error rate by the simple, very simple example of the code that we discussed in the previous example. If you note, this d star for this is 2. If you look at this code, then the minimum weight is 2 and hence D star is 2. So, it is almost like a useless code, but if you see, it has been able to give you a big improvement in the probability of error, residual error probability. So, let us note this thing. If you look at this graph, on the x axis is small p, on the y axis is probability of error, and there are two curves here, one is without coding and one is with coding. Below 0.5, below p is equal to 0.5, we see that with coding is not that effective. Only when you go beyond 0.5 does the coding, so below 0.5 coding has more effect, whereas if the p is much larger, then the coding is counterproductive. So, you should have the channel of certain level for coding to be effective. You just cannot take any channel and apply coding and expect it to be better. So, 0.5 is that tipping point. Before 0.5, below 0.5, yes, error control coding works. Beyond that, it is detrimental. Let us look at another quick example. So, let us say we have a binary symmetric channel with small p is equal to 10 to the power minus 7. What does it mean? That this channel is making a mistake when you send 10 to the power 7 bits, on an average 1 bit gets flipped. So, as such it is a pretty low probability of error. Now, suppose we send 10 bit long words at a time without coding. So, we are not introducing any error control coding, right, and you know any standard modem, it will have its own data rates. So, suppose this data rate is 10 to the power 7 bits per second, which means 10 to the power 6 words are being sent. Why? Because each word is 10 bit long. So, it is a simple example. So, what is the probability that a word is received incorrectly? Well, you can find out what is the probability that word is received incorrectly. Either there is one error, so 10 choose 1, 1 minus p raised to the power 9, that means 9 of them are not in error, p is the probability of error, p raised to the power 1, 1 is in error, or so it is a mutually exclusive event that 2 errors happen. How can 2 errors happen? 10 choose 2, the number of ways I can have 2 errors out of 10, then 1 minus p is the probability of correct symbols raised to the power 8, because 8 of them are correct and p is wrong. So, p raised to the power 2, 2 of them are incorrect, or I have 3 possibilities, or so on and so forth. But as you can see that p is already very small. So, p square is even smaller and p cubed is even smaller, whereas 1 minus p is almost close to 1 and can be neglected. So, we see from this that only the first term is significant and all subsequent terms are orders of magnitude smaller than the previous one. So, approximately we can retain only the first term, 10 choose 1, 1 minus p raised to the power 9 times p, and if you plug in the value very approximately, you can see that this is 10, the first term is 1 and this is 10 to the power minus 7. So, you get 10 to the power minus 6 words per second. Okay. Therefore, in 1 second 10 to the power minus 6 and you are sending 10 to the power 6 words per second will be in error. So, every second one word is in error. Okay. And what is the problem with this is that even if a word is in error, it will not be detected, because if we are not doing any error control coding, any bit stream of 10 bit long is a valid bit stream, but I do not even know whether an error has happened or not. So, one word will be in error over this quite good channel. P is equal to 10 to the power minus 7 is a pretty good channel. but we will not even know, will not even will be able to detect the error, even though one word every second is an error. So now what we do is we add one extra bit. So this example illustrates the power of one bit. Just add one parity bit to the uncoded word to make it 11 bit long as opposed to 10 bit. So what does it do? What does a parity bit do? Parity bit says that one error will be detected. Okay, and even parity will become odd and vice versa. So what will be the case when there are two or more errors? Well, that's when the error will happen. If two or more bits gets flipped, then errors will happen. So how do we calculate the probability of error for this? Well, it is 1 minus probability that less than 2 bits are in error. So the probability of word error can be written as follows. So 2 or more bits are in error, and if you write it out like this, 1 minus all of them are in error, or 2. So you have got this expression and you get 11 into 10 to the power minus 13 if you work this out. So the new word rate, because this one will be able to detect all errors with one bit being flipped. So the new word error rate will be 10 to the power 7 by 11 words per second, because now 11 bits constitute one word, right, and the bit rate hasn't changed. So thus in 1 second, this is the effective word rate into the number of words in error per second will give you 10 to the power 6 words will be in error per second. So how many seconds will it take for one word to go undetected with error? It will take 10 to the power 6 seconds, and which is 11.5 days. Earlier we were making a mistake every second and not even knowing about it. Now we will have that problem once in every 11.5 days. So it has really improved the error detection capability. So this is the power of one bit. No strong coding, no complicated algebra, just adding one parity bit has improved the performance tremendously. So let's look at this very interesting concept called coding gain, because we are gaining so much. Is there a way to quantify it? How do we put it across? So let's have our two most important parameters. One is SNR, which is EB over N naught, and the other axis is my probability of error PE. We would like to define how much gain do we have based on error control coding. So if you look at the graph here, we have on the x axis the SNR EB over N naught, the y axis PE, and we have the blue curve corresponding to the coding, so coded bit stream, whereas the red one is the raw or uncoded bit stream. And you will see that for any given probability of error, say close to 10 to the power minus 5, you can always draw a horizontal line. And what you see is that uncoded versus coded, you get a gain in terms of EB over N naught. This horizontal spacing is called the coding gain, and clearly the units of EB over N naught is in dB. So the coding gain is expressed in dB. If I have a much stronger error control coding scheme, I can have this blue curve shift even to the left, and I can have a larger coding gain. But this coding gain is a function of PE. So only at 10 to the power minus 5 in this example I have this much coding gain. If I have 10 to the power minus 4, the coding gain goes down, and at 10 to the power minus 6 the coding gain is even higher. So coding gain is measured in dB, and coding gain typically increases as PE decreases, as we have seen just now. PE, the probability of error. and the limiting value as p tends to 0, that is very very low, is called the asymptotic coding gain. So, that is the theoretical maximum coding gain that one can achieve. So, for coded systems, coding gain is typically used to compare which one is better. Now, we introduce this notion of perfect codes. So, this is like reaching one of the boundaries, one of the ends of the spectrum. Suppose for any vector u over GFQN and any integer r greater than or equal to 0, the sphere of radius r and the center u denoted by S u comma r is the set nu element of GFQN, given that the distance between u and nu is less than r. So, let us understand what is this thing in Greek. Let us put it back in English. So, we have a code space, and every point in this code space is a vector of length n. Okay. Please note, this is not necessarily binary, we are talking about GFQN. All right. Here we have talked about the notion of radius of spheres. What are these spheres? So, within this code space, centered at any code word C1, we can draw a sphere, a hypersphere, which has several points inside it. But again, each point is a vector of length n. Each of the points inside this sphere will have a certain distance in terms of Hamming distance from that code word C1. Okay. And we are talking about all. Okay. So far, we have accounted for all the points in M spheres. But what is this total number of points, all the red dots and the blue dots and the black dots? Well, all of them should necessarily be less than or equal to q raised power n, which is the total number of vectors in this space. And that is exactly what we have on our slide here. So, if you go back to this slide, we have on the left hand side m multiplied by n choose 0 plus n choose 1 q minus 1 and so on and so forth, less than or equal to the total number of vectors q raised power n in this space. Okay. So, this is exactly what is being discussed here, right. Now, this bound, this upper bound is denoted by a Hamming bound, and this is also termed as the sphere packing bound simply by the way in which this was derived very geometrically. Okay. So, the total number of points contained in all the spheres, decoding spheres of M code words, is less than or equal to q raised power n, the total number of points in that space. Now, this is in general for query codes, but for binary codes things become slightly simpler, and you can always put q as 2, and all of these parentheses q minus 1 goes away, and you get this kind of an expression. Please recall that m is nothing but 2 raised power k. Okay. So, this m can be substituted by 2 raised power k in binary case, but this is the in general. And if you take a log on both sides, then you can write this is m is q raised power k, this is q raised power m. So, n minus k will be on this right hand side, and you have log to the base q, and you have this expression. So, it can alternately be written as follows. So, now we define something called as a perfect code, because we are curious to see whether this upper bound can be met or not, and what if it is met. So, we define a perfect code as one which achieves the Hamming bound, where equality holds. Okay. So, m, which is alternately q raised power k times n choose 0 plus n choose 1 q minus 1 plus so and so forth up to n choose t q minus 1 raised per t should be equal to q raised per n. Any code that satisfies this is the Hamming bound. Now please note m, n, q are all, even t are all integers. So you cannot just have any arbitrary choice of m, n, q and t which will make this happen. In fact, there could be only few combinations of these integers m, n, q and t which satisfy this condition. So let us look at a very simple example. This is our favorite binary repetition code of block length n, and we have taken n as odd. So when 0 is to be sent, 0 is sent as 0 0 0 0 0 repeated n times. If 1 is to be sent, I send 1 1 1 1 up to n times. Clearly the number of errors it can correct is n minus 1 by 2, n being odd, I do not have to put any other restrictions. Why? Well, the minimum distance is n, d star obviously by observation is n. Clearly m is equal to 2, 0 and 1 are the two information words which are being sent. Now we put this constraint and try to check whether it satisfies the Hamming bound. Well, we put left hand side and we find magically we get this repetition code to satisfy the Hamming bound. Thus the repetition code, our trivial code, is also a perfect code. It is a trivial perfect code. Right. So one of the ways to search for this perfect codes is to run a computer simulation to check for various values of n, q, m and t and see what satisfies the equation. And here we have got listed out some typical values found by exhaustive computer search. But please note, just because the values exist that satisfy the Hamming bound does not mean that a code exists. So not for all of these cases a code can be identified which satisfies this condition. So with that we come to the end of this lecture. Let us summarize what we have studied so far. What we have understood is the notion of the residual probability of error. Even if you incorporate error control coding, you can still make errors, and how do we quantify that? So we came up with some expressions and upper bound on the probability of residual error based on d star. Then we talked about coding gain and how it is measured in dB. Then we established a very important bound called the Hamming bound, which led us to the definition of a perfect code. We also looked at some examples along the way. With that we come to the end of this module.